Yes, so we've been doing work on the Galactic Center, in my case, over 35, 40 years. And I'll tell you in an introduction what drove us, in fact, Charlie Towns at the time, to start with that. And we're still on the same road and continuing. And dare I say, I predict that even after my passing away, that will very well may still be the case, because this is really a laboratory which rarely you get in astronomy, as you will see. Normally you get systems which are very complex, such that if you're looking for physics, may be hard to get at. So I'll try to give you the story as it stands, with a major breakthrough happening in the last 2 years. So that's some of my team members. The Gravity collaboration is a collaboration from several institutions led by Frank Eisenhower here, who's an outstanding world-class experimentalist, physicist. So MPE is the host institution. Then we have the Max Planck Institute for Astronomy in Heidelberg. We have the Observatoire de Paris, the Observatoire de Grenoble, SIM in Portugal, Cologne University, and then of course the host institution is ESO, because as you will see in a little movie we made, to get to the detector from outer space. My ears are too large or too small? The head is too big, yeah. Am I okay now? Yes. So as you will see, you know, the experiment we have built really spanned the entire VLT telescope area, and so ESO's participation is crucial. Now, in view of time, let me just give you just 3 slides as an introduction. Of course, the first one is the theory, Einstein's work, the 2 solutions, spherically symmetric solution by Karl Schwarzschild already in 1916, and then the solution with spin by Roy Kerr. And really, since astrophysical black holes, for all practical purpose, don't carry charge, these are the 2 quantum numbers we need to know, at least if Kerr's solution is the unique solution, mass and spin. And so, from a physics point of view, of course, you would ask the question whether such objects exist in nature and where they might be. Then, from an astronomy point of view, came the discovery of the quasars in the same decade, in fact, when Roy Kerr found his solution. When you talk to Kerr, personally, he would tell you that he didn't know anything about the quasars, and the quasar people didn't know all that much about Kerr. That happened later. But certainly it was clear when the quasars were discovered that such an amount of energy, as seen in the first object, 36273, at redshift 0.15, that if the distance really was 2.5 gigalight years, well then the amount of energy radiated of 1,000 times the Milky Way within a very small fraction of the area of a Milky Way, that this must be a very high energy density, which the theorists at the time immediately found could not be supplied for any length of time from a normal fusion star cluster type system. So in order to get to this much higher energy density and efficiency, surprisingly, massive black holes might be a solution. And the basic idea is that at the last point where in GR stable solutions for particles are possible, you can release between 15 and 40% of the potential energy, gravitational energy, into radiation. So that's a much higher, by almost 2 orders of magnitude, efficiency of radiation than in fusion, where it's 1% or less. So that's why the massive black hole paradigm, already in the early 70s, here's a famous paper by Lyndon Bell and Rees, became sort of the the mantra almost. It was sort of assumed to be the most likely situation. But from assuming a most likely situation and telling everyone that you think it is to proving it is a wide difference. And so, in fact, it took quite a while until the first steps were taken to try to prove the concept of these massive black holes. And clearly what you have to do is you have to spatially resolve the gravitational potential of an object and then come as close, well, as the event horizon, which is predicted in general relativity, and show that all the mass is within that event horizon. Then you're sort of close. You still don't know whether that's a Kerr black hole. Then you really have to show more, namely that mass and spin are the only quantum numbers to explain, for instance, the quadrupole moment. Then you are, with this no-hair test, then you're really in business. Unfortunately, with quasars, you can't do any of this. They're far too far away, at least at that time, to make any meaningful spatially resolved measurements. And so, in fact, that paper in 71, Rees and Lindenbell already had the word galactic center in there because the galactic center is, 4 or 5 orders of magnitude closer than any of the objects which are in this category of quasars. So maybe that's the way to go. Although the galactic center is not a quasar, maybe it might still have a black hole in it. That was the idea. And so then in the following decade, the radio astronomers discovered, in fact, then a compact radio source, Sagittarius star, in the middle of this central region of our Milky Way. So that could be the center around everything. The next step, however, required new technology. The galactic center is very close, 26,000 light years away, but it's unfortunately between us and the galactic center is a column of dust in the Milky Way plane, which is about 10 to the 12 in attenuation in the optical. So you cannot see the galactic center. It's not practical, not even today. So you have to go to longer wavelengths where the dust is less efficient in absorption and extinction, and or shorter wavelengths where dust doesn't play a role. So X-ray astronomers can look in the galactic center, radio astronomers can, infrared astronomers barely, and optical astronomers, as I said, not at all. So Charlie Townes, famous for his Nobel-winning work on the maser and laser, in Berkeley in the 1960s and early 70s, started to get interested in this project, in this problem. And likewise, down at Caltech, Gary Neugebauer and Eric Beckman, his student, also started to get interested in the galactic center. They then proved by infrared measurements that the galactic center actually was a very, very strong source in the near infrared, and showed that this was due to a star cluster of about 10 million solar masses over several tens of parsecs. Townes then built a spectrometer for 10 micrometers, so in the mid-infrared, to do spectroscopy of line and a fine structure line of ionized neon to show that as one stepped in the innermost region, here's the radio map, where this here is the radio source Sagittarius star, which I already mentioned, that if you step along this streamer of plasma, which is ionized hydrogen, that the motion, which you can see due to Doppler shifts in the line of neon 2 of these gas clouds is huge. It's several hundred kilometers per second. So if you use virial equilibrium, square the velocity times the distance over gravitation constant, you get millions of mass of the sun, all contained perhaps in this innermost region of a few light years. So that was the first step leading to ever better measurements of the gas. So by early 1980s, when I started working in the project, we were pretty convinced and wrote a Nature paper that the galactic center had a black hole of 4 million solar masses. So why didn't we stop? Well, hardly anyone believed it because gas you can push around with gravity, of course, but also with winds from stars. Also, magnetic fields could push around the gas. So it's not immediately clear that the interpretation that this is a virial equilibrium or an orbit or something like was possible. I then left Berkeley, as Amiel mentioned, to Munich. And so in Munich, we started building instrumentation in the near-infrared, which for the first time looked at stars spectroscopically. And stars are good probes of gravity. And also worked in the near-infrared and worked in imaging mode so that you can actually do spectroscopy and also imaging at the same time. So that was the start of our journey toward the galactic center. And our quest of 3 decades used then this facility, which is the ESO, the European Southern Observatory, Very Large Telescope. This is in the Atacama Desert. That's a real desert. I mean, there is nothing which grows there, really not, even if it rains once. And so this is at 2,600 meters altitude, right next to the ocean. The ocean is only 15 miles away. So there's a very laminar flow here, very good seeing, and incredible good conditions for clear skies. So you see there are 4 telescopes up there, 4 8-meter telescopes. And ESO, wisely convinced by very wise people at the time, said, well, let's put them there in a way such that you can actually actively combine the light of the 4 telescopes for spatial interferometry. That at that time was a bit of a dream, and nobody really believed it would become possible, and I'll tell you in a second why that was. But this foresight is essential because that put us in the situation of basically using this facility for us. Actually, you will see later on that underneath this platform there is a tunnel down here, 200-meter long tunnel with little carriages driving, which serve to compensate for the geometric path length. So if this telescope looks at a star there, and this telescope looks at that star, then there is a difference in path lengths here, which you have to compensate for in order to combine the light. That's the famous delay, a geometric delay, and so you have to actively, work to make this system do whatever you want to do scientifically. So we started with a system doing speckle work, not on the VLT, that didn't exist at the time, early 90s, but for the first time with a detector which allowed us to do so-called speckle imaging. So you basically froze the Earth atmosphere turbulence by very rapid imagery. Then in 2002, we built a first camera with adaptive optics. So that basically corrects for the disturbances of the wavefront, which is due to the atmosphere, by direct measurement of the wavefront and then basically having a deformable mirror online flattening the wavefront back to a hopefully optimum situation. Then a few years later we put Symphony on the telescope, which again is an adaptive optics instrument, but this time to do imaging and spectroscopy at the same time. So for each pixel in a group of pixels on the sky, you get both an image, two-dimensional image, but also many slices of spectra, so you can look at spectral information. The next big step was adaptive optics. It works well if you have an object which you can assume to be a point source near the source of interest. Perhaps the source of interest itself, but at least a bright enough star that you can use its light to analyze it and do all of the necessary wave analysis to do the correction. Well, that's a pretty bright star you need, and the probability to find such a star close to the object is fairly close to 0. So the next big step in the field involved bring your own star. So basically, we developed a laser system. You see, it's yellow. It's basically on the wavelength of sodium D. You shoot that out to 90 kilometers altitude, where there is a sodium layer due to the meteorites basically raining down on the Earth, being destroyed, and then the atomic sodium we can excite, and the backscattering, the resonant backscattering goes back to the telescope, and you analyze that artificial source then and correct for the wavefront. So that's steps we all did in the 1990s to the 2007 period. And then at that time, as you will see in a second, we already had very nice information on the stellar motions and very strong evidence that there might be a massive object in here. And we then said, well, if we now want to turn this around and play with the object as a physics experiment and use it to test general relativity, which is sort of one of the dreams, then actually you have to have still higher resolution and combine the light of all of the VLTs. So that we started doing in 2005. It took us 12 years to build this machine, Gravity, which then came into operation in 2005. And you will see why that was important, because one star plays a very important role here, which we knew would be coming back for a very close encounter with the black hole. So here's the sort of the summary scientifically of these first years. You see the orbits of stars we measured. Now we is a group of young people and not so young people in Europe, but also the group of Andrea Ghez, who parallel and independent of us worked at the Keck Observatory. So there was a international competition, if you like, very good for the onlookers, because they could check us at any time. If you agreed, everyone could check, must be true. If you disagreed, square, more work to be done. So as I said, by about 2005, it was clear, in particular from the work on this star, which was on a rather incredible elliptical orbit of ellipticity 0.88, as you see here, coming by as close in 2002, as close as 15 light hours. So that's 4 times the orbital radius of Neptune, so about 200 AU, incredibly close on standards of black holes and galactic nuclei. And so the star here is moving at about 8,000 kilometers per second, so 2.5% speed of light. So that seems like a wonderful occasion to measure deviations from Newton and Einstein. So we knew, well, roughly 16 years later, we've got to be there here with our new instrument. That was our motivation to work hard and actually be online. And we did, So that was the first phase, as I said, and then both teams got to work to prepare for the next one. But now let's look at tests of general relativity in a broader sense. Why? I mean, GR has been tested so many times. In some newspaper articles you hear, I'm going to get puking if I hear another thing about this. Well, let's be careful. First of all, the tests, many people understand tests, so to speak, the continuum of curvatures of space-time, where then the event horizon, which is up here of a black hole, would be sort of the extreme curvature you can get to, because once the object is beyond it, you don't have any communication anymore. So indeed, over the years, starting with the famous Pound-Repka laboratory experiment at Harvard, ever better experiments than in the solar system, then higher order terms like the Shapiro delay, then the first pulsar work, always stepped along this ever higher into the regime of curvature, and GR was shown to be correct. And then this culminated a few years ago, 2.5 years ago, by the detection of an inspiral of what looked like 233 solar mass stellar black holes with LIGO. So, aren't we done? Who of you who've heard about this thinks that LIGO has proven that these two objects are black holes? Who of you thinks that they have done that? One, at least one, two, come on, 3, 4, oh, all of you must believe that. Absolutely not, okay? Absolutely not. There's one thing to say, and that's what the papers say, the data are consistent with. Yeah, that they are. But to prove that the gravitational wave event was truly a Kerr black hole, you need to go much, much deeper. And in fact, the chances are that this will not happen with LIGO, because you need to define the geometry of the system so well that you can really measure with high precision the incoming two binary objects and their orbits, and then measure the quasi-normal modes of the ring down with high enough signal-noise ratio that you can exclude all other options. And so that is predicted to happen in an extreme mass ratio in spiral with LISA if it flies maybe in 25 years, but not with LIGO. So please, I mean, if you're friends from gravitational waves, I honor them greatly. They do fantastic work, but they've not proven that these objects are core black holes. Then the next thing is mass. There's a second dimension here. We don't know that GR is not mass dependent. In fact, there are some other theories of gravity which are mass dependent. So we want to also explore something which has much greater or much smaller masses. In fact, the detection of broad iron K X-ray spectral line emission in some AGNs, if you believe the interpretation, is a first test of that type, fairly close to the event horizon, actually. Unfortunately, of course, this is not a direct measurement. It's not a measurement. It's an interpretation of a model, namely that you have a gas swirling around such a thing, and then you can use the red shifts you measure to infer the depth of the potential. So what can the galactic center do to add to this? Well, first is, of course, the stars we know. We know because of our work over the last 2 decades. And in particular, this star S2, which comes close enough that it's right here. So that's, in fact, already fairly relativistic, far more relativistic, by the way, than any pulsar work, okay? So we are probing the potential both at high mass and at significant speed. 2.5%, 2.6% speed of light. If there are other stars, which we don't know yet because we have not been able to probe these closer in, then these would even be able to sense the spin of the black hole due to the space-time dragging and quadrupole of the black hole through the lens tearing precession. So that would be somewhere in here. And then finally, as you will see, we have seen the black hole itself radiate infrared emission. Polarized synchrotron emission from hot electrons, which from their variability point of view might come from within, in the innermost stable orbit or around there. So that would be way up there. So these were our 3 motivations back in 2005. And at this point, we've done these 2, and I'll report to you the results. This one is still outstanding, and we are looking. And it's just a question of how deep we can push the imaging. Now, let me tell you a little more about the issue why this is also difficult. If you want to bring 2 waves to interfere for spatial interferometry, then, of course, as I said already, you have to bring the wave to properly interfere at the same point in the wave train. Okay, so you have to correct for that geometric path length difference, etc. And you have to do it properly on the fringe. Now, the fringe is, so to speak, the maximum contrast of the interference pattern in a positive sense. Now, when you have light at some wavelength and you now have a bandwidth of light, then the fringe, as a result, becomes narrower and narrower. While if you have a monochromatic ray, of course, then you have basically a sinusoid. So the wider the bandwidth, the more difficult. The radio astronomers work with relatively narrow bandwidth. So their fringes, because they are long wavelength and narrow bandwidth at the same time, are very wide, so to speak. In the radio regime, the fringe, the coherence pattern, is about 60 centimeters. In the millimeter range, it's still a substantial number of centimeters. So it's easier by that factor of the ratios of the wavelength, and then also another wavelength term, to get the fringes. The next one is the coherence time. Atmosphere moves, and the coherence time in the radio is fairly long, minutes. In the millimeter range, it's still tens of seconds. In the infrared, it's 1 millisecond. Okay, so that means we have to have done everything, like detecting the fringes, in a millisecond. The next one is the brightness of objects. Now, the radio astronomers often look at very non-thermal sources, high temperature, unfortunately at low frequency. So here are various factors which now begin to compensate. They look at bright sources. We look at thermal sources, which are less bright, but at higher frequencies. So some of these terms cancel. And finally, there's the issue of transmission of the instrument, quantum efficiency, etc. If you put this all together, the factor is roughly 10 to the 5. So it is roughly 10 to the 5 times more difficult to produce this technical interference in the infrared than in the radio. So that's the main reason why all these years, you haven't heard about famous discoveries in interferometry in the infrared or optical, for that matter. The next one is the Nobel Prize was given for the discovery or the development of aperture synthesis interferometry. So there you don't look only to Martin Ryle. There you don't only look at the interference between two telescopes and one combination, but you have a number of telescopes, and to make all these different combinations gives you a coverage in the so-called UV plane, and the information in the image plane is the Fourier transform of this. So the more of these UV planes you have, the more interference points you get with n telescopes, n times n minus 1 over 2 combination of visibilities, the better you are in terms of the imaging. Maybe, maybe not. This works only if by splitting up the light, you don't lose signal. And that works in the radio because there are amplifiers, phase-sensitive amplifiers in the radio, which don't lose you light. In the infrared, an optical doesn't work because there's so-called quantum noise. You cannot amplify the radiation without getting an additional term into your signal, which then basically demolishes the amplification. So you cannot amplify. So when you split, you lose signal-noise ratio at the same time. So to build a VLA or an ALMA antenna in the infrared is not practical. So in that sense, 4 telescopes is about as good as you can do. You have lost already some light, but it's not damaging to. So that's basically why it took so long. Now, with 4 telescopes, of course, you would at first think, is your beams look terrible, the beams being the Fourier transform of the UV coverage. So this is the east-west, north-south coverage of these baselines. So, every wavelength forms a sort of a track here, and then, the different combinations give you different tracks, and then the combination here gives you beams with these ugly side lobes. Fortunately, we have wide bandwidth. And because we have wide bandwidth, our UV tracks are radially much more extended than radio tracks. So our coverage of the UV is much better than you might think at first. But that is what happens. The beam formation then delivers you at 2 microns, a 2 by 4 milliarc second, typically in the galactic center, a 2 by 4 milliarc second full width half max positive interference beam surrounded by crap of side lobes. So that's the physics of all this. All right, so in gravity, in this instrument, we needed to put all kinds of innovations in order to make this really possible. The first one is we built in industry a imaging detector at 2 microns, which essentially at 1 kilohertz, 1 millisecond in coherence time, has no read noise anymore, 1 electron. Then we had very compact optics. We put the whole beam combination into a cryogenic environment. In the olden days, you would go into the combination laboratory, you would find all these optics along benches, which is not what you want to go with. So we put it all in a door and made it compact by bringing the light into monomode fibers. The fibers also immediately filter the light because they're only sensitive to one mode. And so by aligning the modes, you're immediately fully coherent. So that's a very, very good thing. And we have adaptive optics for each of the telescopes, which in principle deliver 50% strail, where 100% is the best. Then we send back through the instrument, I don't want to go through the details, lasers everywhere to measure distances and correct for the changes in numbers and so. And then in the end, we have a system which can do imaging, spectroscopy, polarization, etc. Fairly powerful thing. And indeed, this is quite something. 10 microarc seconds, which is what our goal is, to resolve, so to speak, the event horizon in the galactic center is 10 microarc seconds. 10 microarc seconds is 2 centimeters on the moon. So when trying to show this to the public at large, one of our speakers from ESO basically went in and made this plausible through a football match, where we would, with gravity, be the recording judge for the fouls and so forth, right? And so for that, you have to, resolve roughly, a few centimeters. Okay, last slide on the instrumentation. I do want to bother you with this little movie we made to show you the pain of the photons as they are squeezed through our apparatus. So this is called the last millisecond of a photon. So here we are, arriving from space, going down in the Atacama Desert. That's UT1 hitting primary, secondary, tertiary. Now we have to bring it down into the beam combination laboratory. So we have to go through about 10 mirrors, unfortunately, to bring it down. No way around this, losing some light in the process. Now down there, we actually have our adaptive optics sensors, as you will see in a second here. So here we are analyzing the wavefronts for each of the telescopes, each of the beams, and know then what corrections we have to use. Then we come with our beams along into the tunnel. There, the carriages are at work to compensate for the wavelength differences and the geometric path difference. And then finally, we come into the beam combination laboratory. Finally, the photon is beginning to see what is going to happen to it. It's going to squeeze into this door at low temperature. Here we're doing some analysis on the optics, also corrections, tip tilt, and so forth to make the images fully correct in the image and pupil planes. That done for all the 4 beams. And now we pick 2 positions on the sky, one for the fringe tracker and one for the science object. And both of these, for each telescope then, as you will see in a second, go then from now on into fibers. So from here we are in free optics, and then we are going from here into the monomode fibers, which allow us to do all kinds of tricks. Like, for instance, when we then discover the fringes, measure the fringes on the bright object, we know what we have to do to be coherent on the second object, and we achieve this by stretching the fibers just a little bit, okay? So here we are in the fibers, there you go. Now you will see a coil of fibers, or maybe you've already seen it, maybe when I was, there it is, there's the coil of fibers. Then we can also torque the fibers to correct for polarization. And then finally, after a few more of this, we need to make the beam combination. The beam combination is done in a very clever modern way to go into a chip, into an integrated optics chip. There it is. It's about yay big in size. You come in with 4 input beams, and you make all the combination on the chip and come out with 24 output, sampling the full fringe and all the combinations. And finally, you go through a spectrometer and spread the light in wavelengths. The photon is dead. All right, so that's gravity. So you will be able to use it. So let me then give you our results. So let's talk about the first experiment, which is the object S2, the star S2, which we first measured in '92 up here with the speckle technique. And these are the red points. And then it made its first Perry passage here in 2001. Our colleagues from the Keck also started with the Keck telescope, observing in '95, that's around here. And so they had the same data set from their perspective. Both saw the Perry, measured the same orbit more or less. Then it was going back out. Both teams with adaptive optics followed, the travel back out. Here we are now in 2008, 9, 10, 11, back at Apo. Apo is around here, and then coming back in. And as I said, we knew 16 years later we'll be there again, and that's when we have to be ready. So we delivered gravity to the telescope here at the end of 16, and we were just ready for the first passage here in 17. So we were covered with gravity now, this entire arc, the most important part of the orbit here. And indeed, it's quite a difference. This is diffraction-limited AO imaging of the region with NACO or the Keck instrument, NERC2, and you basically see, 50 milliarc-second little images here, already cleaned in many ways. I mean, so you remove the side lobes, etc. And you see the source is a little elongated here in March, and that's because actually there's two sources there. There is S2, and then there's the black hole. That you don't see with adaptive optics because they're smeared together. Now we're switching on gravity, and you see there's the black hole, and there's S2. So you can easily distinguish the two. So that's the kind of data sets which we started taking since 2017. And so where previously we would see the star move on the sky significantly only in, well, somewhere between 6 months and a year, we would, with gravity, do this in one night. Okay, so in fact, of course, around Perry, it moves pretty quick. Here it moves about 500 to 500 microarc seconds per night. And so you can easily see this between the different days here. These are measurements with gravity as it goes around Perry. Perry was on the 19th of May last year, where the approach was 14 milliarc second, or that's 1400 Schwarzschild radii around that black hole. So that was the measurements done astrometrically, and all of this to a precision of about 50 microarc seconds, 50 microarc seconds, roughly, on average. Now, I mentioned already the issue of a third star, and so this has been on our minds, of course. Is there possibly anything other than these two objects? So let's remove them from the image as best as we can and look at the residuals. And unfortunately, so far, we have not seen anything down to about 21st magnitude. And please appreciate, this is 10,000 times fainter than any astrometric, interferometric imaging which had been done previously. So now we would expect at that level maybe to see a star just from extrapolations, but we need to look harder, and perhaps next year or this year, when then S2 is a little further away, it'll be easier to see a faint third source. Then we are looking at this whole thing also in spectroscopy, because the first GR effect, as you will see in a second, is an effect which shows up as a change relative to Newton in the redshift, okay, the gravitational redshift. That's another way to say this. This is the famous effect of the clocks going slower in one reference frame relative to another one. So here's the spectra. The star, basically has changes wavelength or frequency in terms of velocity about 6,000 kilometers per second. In fact, the Perry time is here. It's not at the peak. And between that point and that point is only 2 months. So that's another interesting part of the orbit where the change from night to night in radial velocity is 100 kilometers per second, which is easy to see with our techniques. We are using these lines here in the near infrared. There's a hydrogen recombination line due to Bragg gamma, and there's also a helium line, and basically we are cross-correlating this pattern which you get after many iterations with the data you take. So that's the way we get data. So we have spectral data and we have astrometric data. And the improvement has been very substantial if you look in the end at the parameter estimations, as you will see. So for instance, let me just pick one, which is the period of S2. So before 2002, 1 or 2, we didn't know, of course, anything because we didn't know that the star was on an elliptical orbit. But then, in 2003, after the first Perry, we knew it to about half a year. And that improved slowly over the years. But then with gravity, within 2 years, we came down from days or weeks to hours. So we're now at 9 hours. We know the arrival to the accuracy of 9 hours. And that accuracy is needed to see the effect. because the GR effects are really subtle. They are really subtle. So if you look in redshift, for instance, here is the expansion in terms of it's so-called post-Newtonian expansion in terms of beta, beta being V over C of the star. So you see this term here is the Keplerian motion. Okay, and then the first GR term is beta squared here, is actually a sum of the tangential Doppler, so that's a special relativity effect, and the gravitational redshift. That's a true GR effect. They're equal in magnitude, and for the object we have, beta squared is 6.7 by 10 minus 4, so you have to measure to a small fraction of that in order to see the effect. So that is why it's not trivial at all. So here, if you expand to higher orders, you get all kinds of effects which GR would predict. The first one is the so-called Römer effect. That's almost trivial. That's just light travel time. Okay, it takes if the star is behind the source, it takes a little longer to come to us. That's substantial and needs to be taken into account. See, that's up to about 50 kilometers per second, and also astrometrically, that's important. Then the next term is the gravitational redshift plus Doppler. That's 200 kilometers per second. The next one would be the spin. Unfortunately, for the orbit of S2, that's less than 1 kilometer per second. So that is out of the reach of the experiment. Then there are higher order effects like space curvature itself, the delay due to space curvature. That's Shapiro, delay of the geodetic path from a straight line, and that's also only a few kilometers per second. So really, we knew the best we could do is go to this term here spectroscopically. Then I come back to this when the first precession term astrometrically shows up. That's the so-called Schwarzschild precession. All right, now, the first way to analyze this, you would think, is the following. You go ahead and you measure the orbit with all the astrometry you have, and you take in also the spectroscopy, accepting the period around Perry, because the effect of general relativity will only be significant in that period. So then you generate a prior by fitting Kepler to all the data, the astrometric data, plus the frequency, the spectroscopic data, accepting the near Perry data, and then you basically say, well, if I now take that prior and extrapolate into Perry, are the real data generating a difference? And the answer is yes. Well, are you done? No, because the parameter correlations post facto allow you to talk around the Kepler parameters, and in fact, if you don't have gravity, don't allow you to properly exclude degenerate Keplers, which you would not have considered otherwise, but you need in order to understand the GR effect. So you can make the GR effect go away unless your astrometry is not good enough. So that's something we really appreciate fully only in March last year. We were very glad to have gravity, because without gravity, we would not have gotten the result we have now. So what you do in the end is you do a Bayesian post MCMC fitting. You need 14 parameters at this point, and here is the key parameter. This xg or f is that factor which for Newton is 0 and for GR is 1. And so here you see for this fit here we are 1.01 plus minus 0.05. Okay. If you've seen our paper in July last year, there we weren't quite as far, because of course we only had data to July's, and then we had 0.9 plus minus 0.01. So the data for the rest of the year still further improved the fit. So these are the residuals from a Newton orbit. So here you see the data relative to the Newton orbit. There is the beautiful excursion due to the gravitational redshift and Doppler. And you can see that in the two astrometric residual plots, there's nothing which really see. You see some interesting effects which our colleagues also note at Keck, which is you see non-Gaussianity excursions in these plots. That's due to confusion with other stars which were not known. So if there's a faint star which you wouldn't know about passing through the orbit, then that pulls the light center just a little bit, say half a milliarc second, but it does so for a number of months or years, such that in the end that you see these long wavelength scale residuals occurring. So we know therefore that this GR passed this at 20 sigma roughly, and in fact that gravity is essential to remove these degeneracies, because otherwise you would say, why do you need astrometry if you see the entire effect in wavelength space? And we now know the black hole mass to about 0.5%, and the galactic center distance to 0.2%. That one is neat, because we weren't pushing for that, but it came out really rather nicely. I should comment that our colleagues at Keck now have also a result. Of course, they don't have gravity, so their result is not as significant, but it's somewhat consistent with that. Unfortunately, there is a tension, as you will see when the paper comes out, in distance. And we will still need to iron that out, why that might be the case. Okay, so that's the gravitational redshift. What's the next one? The next one is the Schwarzschild precession. So that basically says that if you have no extended mass distribution, the orbits are not closed, but basically precess in plane, in the case of this object, by 11.9 arc minutes per revolution. You would think we could do that over a long period of time, and so that you could ask, well, why haven't we measured this? Because over a 16-year period, we are just not able to fix the reference frame well enough or long enough that we can measure 11.9 arc minutes. But because it's a highly elliptical orbit, and this depends so strongly on RS over A, the Schwarzschild precession actually is largely occurring near Perry. So that's this term here. You see, this is the Keplerian, if you like, or if you don't include the Schwarzschild precession term, and this is the Schwarzschild term. And you see how this angle here is due to the Schwarzschild precession, mostly in RA. And that, in fact, we will try to triangulate now this year and next year. So our forecast is that by hopefully the end of this year or perhaps next year, we have a 5-6 sigma result on the Schwarzschild precession. So that was the first experiment successfully done. Now, if you recall my slide of the various other possibilities, one was to look at the gas very close to the black hole. Now, that was sort of a dream. In fact, in 2005, Avi Loeb and Broderick basically took us, our suggestion at face value and made some GR models of if there would be sort of a compact emission spot in the infrared, variable emission spot, which would orbit in this innermost region, whether this could be used for GR physics. And the answer is yes, if it's stable enough. That it won't be, because there is no self-gravity, so any gas blob you generate will be sheared away into a sort of an arc. And if it follows the innermost circular orbit. So this is really the assumption. Now, do we have reason why that could be? Well, the infrared emission from the black hole itself over time is a highly red noise power spectrum, as you see here. So it varies by many orders of magnitude. Sometimes, gigantic spikes of emission where the emission is brighter than S2 itself. And the interpretation we have for this is a bit like a solar flare. The idea is you have a magnetized plasma, and in this relativistic magnetized plasma, you get local reconnection. That's the idea. And the solar flares here in these loops here, they cross and they combine and thereby accelerate electrons. And we need that because the virialized electrons in the innermost ISCO region have a gamma of 10, so they would not make infrared synchrotron emission. To generate infrared light or even X-rays, which is also seen, you have to have gammas of 1,000 or maybe even as high as 1,000,000. And that can perhaps originate in such reconnection events or in shocks or other localized events. So that would generate naturally spots. And if they then, so to speak, would move along in the plasma, then you could use them at least as somewhat plausible clocks moving in the orbit. Not very stable clocks, but at least you could use it. So that's the idea. Over the last 10 years, I should say, we lost our faith that that would likely happen. The more we were surprised than when we recorded our first 3 flares with gravity to see patterns like this. So there was a flare of about 30% the intensity of S2, pretty good flare. And it started here. There's the black hole. Of course, there are errors, which are substantial. And then this flare moved around on the sky like this. Now the error bars on the positions of here versus this was only 20 microarc seconds at the time. That is because we are now looking in the flux distribution of the black hole, which normally has very faint magnitudes. So that's down here. We are now looking here. And that means we have such a bright source that we don't have to integrate very long, and we get high signal noise ratio. So that's why we can get very precise relative astrometry between the black hole and S2. Then we have to remove, of course, in the data analysis, the motion of S2, its orbit, and then infer this loop motion. So in this one flare, we see what appears to be a loop motion on a scale of about 100 microarc seconds over 40 minutes. That's third speed of light. Okay, that's third speed of light. And then we saw 2 more such flares, just like it, same sense of motion on the sky, same projected radius, same time scale. That was somewhat encouraging. So that's sort of the picture you would send to your press agent. And indeed, it's a fairly simple thing, remarkably. Even I, without much ray tracing codes available, but just a spreadsheet, analyzed the data. I assumed this was a normal ISCO, and I assumed naively it was face on. Wait a second, why face on? Well, that's what I did. And you'll see why. And then, in fact, these are just nice sinusoids, and you know, the relativistic time delays, they go all the way in face-on orbits, no problem whatsoever. And so you can, on this, either with your ray tracing code, bring it please, or I, with my spreadsheet, we got the same answer for a face-on orbit, which is 7 RG, or 3.5 Schwarzschild radii, so that's 1.2 ISCO. Ooh. And that 3 times. So that was fairly encouraging, I have to say. And then came the next thing, is we are able to record the polarization of these light spots, both U and Q. And in one flare, here's that flare, which was actually double humped. Again, you see in the polarization degree, direction. Again, in the 2 directions, sinusoidal pattern. That means that the polarized direction on the sky is rotating smoothly 360 degrees. Fantastic. People had been trying to look for this. In fact, in Maroney's PhD thesis, he was dreaming about this already in 2006. There it is. Beautiful loop all around, or more than one around actually in this case. And that's the key thing, the orbital period and the polarization rotation period are identical. Now that is not what you would have expected, because if the polarization follows a magnetic field, or is perpendicular to a magnetic field, which you would say is in the plane of the orbit, which almost everyone in the field would have expected, then the polarization loops are twice as fast as the orientation. So we are learning something about the polarization physics and the magnetic field structure in this innermost region. And Jason Dexter showed very nicely that very likely what we're looking at is a poloidal field, so a very strong field which is perpendicular to the orbital plane of the gas, probably along the spin axis of the black hole, and modified by light bending effects somewhat. And then you can understand why you would see these single loops. So let me summarize here. I'm trying to tell you, we have this incredible luck that we are looking at the galactic center, down the barrel of the spin, and possibly the jet, and looking more or less face on at the orbit of the gas. What is the a priori probability that this would be the case? 0. Okay, absolutely 0. Here's the arguments why it's true. First of all, I told you already the polarization period can be understood in this way, and that basically constrains the polarization loop. The next thing is the contrast. So if you have an edge-on situation with a 30% speed of light, then, of course, whenever the gas comes at you, it's Doppler boosted. Whenever it goes away from you, it's anti-Doppler boosted. So if that happens, then always on the one side of the orbit towards you, you should see a tremendous increase in sensitivity. We don't, in none of these flares. And so if then this boost is less than a certain factor, let's assume 2.5, that immediately shows it cannot be edge-on, it must be face-on. And finally, the astrometry, just from if you do the fitting, that gives us a sort of a confidence interval over here. So roughly speaking, we are in a situation where the inclination is less than 30 degrees, and the radius is somewhere around 7 to 8 gravitational radii from all these arguments. Now, there is one additional wonderful recent result from the VLBI community at 3 millimeters. This is not the Event Horizon team, but is a related team working at 3 millimeters, and they measured the size of Sagittarius star. You have to correct for scattering by the electrons in the foreground, etc. I don't have time to go into this. They measure sizes which are rather similar to our sizes, okay? And they see the object to be circular. In fact, in their paper, they show if it were on jet, if it had a jet and would not be face on, you would be inconsistent with this image. So either there is no jet, or it's circular because it's face on. So that could be very well in agreement with what we have. It's very encouraging. So finally, then, let me summarize here. We learn from these 3 flares that we have what looks like face-on orbits whose formal solutions in period and radius you see here, somewhere around 40 microarc seconds in radius, somewhere around 40 minutes in orbital period. And that is what you would expect for a 4 million solar mass black hole if it has no spin near at ISCO, and then when you march out in radius here, or if you have a maximum Kerr hole, that's the ISCO here, and then you march out in radius. And if you're on a retrograde orbit, maximum Kerr, then you're on this here. So you see, all these 3 flares in their periods and radii are very well consistent with the 4 million solar mass black hole. The same 4 million solar masses we measured with S2 to 4.5%. So in fact, the mass measured, so to speak, is between 3 and 5.5 by 10 to the 6 at ISCO or near ISCO. And then comes the polarization periods, and again, gives you the same kind of information. Now we need to repeat this experiment, of course. We will try this year. Our first run is in end of March. So we'll see whether we're lucky enough to see more flares and can confirm this picture. Unfortunately, this time, our colleagues in California cannot help. I mean, they don't have gravity. That's sort of not good because, I mean, would you trust the Europeans to do anything right? So how have we come in 35 years? Well, when Charlie Towns and I published an annual reviews article on the case, we just then had the first indications from the gas motions that there was inside of a parsec no fall off of the mass anymore, but it would sort of be steady at around 3 million solar masses. So now we've pushed that region, which we had then, by a factor of 1 million in. Okay, so we measured stars, several stars. We measured S-star orbits. We measured the peri of S2. And now we measure that flare, if you believe what I just told you, all indicating the same mass to within the uncertainties, down to the event horizon or a few times the event horizon. So looks like an elephant. Is it an elephant? Well, you recall my earlier question. Do you think this shows that this is a Kerr black hole? No. I'm afraid not. That is not good enough. But it certainly is a good start. But it shows you how difficult it is to actually do the ultimate proofs on this. Here is a path which could be taken. This is my last slide, I think. This could be a path to the ultimate Kerrness test in the galactic center without gravitational wave, in spirals, and all of this. So one thing is that the Event Horizon Telescope, working at 1 millimeter, will measure the photon ring. So that's actually pretty much the same angle as what we are looking at. So, yeah, pretty much the same region. But this ring, indeed, is dependent on the spin, chi, and also any deviation from the Kerrness in quadrupole moments. So in principle, by measuring the shape of the ring well enough and showing it's not circular, it's not deformed, then you can make a statement on this asymmetry, and this asymmetry then can be turned into a quantitative measure of non-Kerrness. If then gravity and symphony continue and find a third star, then we can measure the spin. With S2 we couldn't, as I mentioned to you. So here we've done some forecasting. Edel-Weisberg showed that if we had a star at about a third distance from the black hole, then we could measure the spin after a few years to 5, 6 sigma. So you put this all together. This is what the event horizon would measure. This is what we could measure. If you then, in addition, find a pulsar in here, which the radio astronomers are trying very hard, that would look like here. So Kerr is right here. So in principle, if everyone works together, and we are extremely lucky, especially with the pulsar, of course, we might be able to do a no-hair in a decade. But I'm a pessimist, and I would say that's for sure not given. Not that you think that the gravitational wave people are in any different shape. I mentioned that before. It's really very difficult. Okay, so that was our journey to this point. There was many other science results which we've been able to get on AGN and in exoplanets and so forth. So this new technique, which is an old technique, is really now in full bloom. I thank you very much.